Hi everyone, this is the last section of notes for Chapter 2, and this Section 8 is titled Proving Angle Relationships. So just like the last section where we were doing proofs with segments, this section is going to do some proofs with angles. First, let's talk about a few postulates and these things that we've already looked at before in Chapter 1. The first angle postulate is the protractor postulate, and it's similar to the ruler postulate that we just went over, and all it says is that we can measure angles using a protractor, and there's a one-to-one correspondence of a given angle measurement to real numbers between 0 and 180 degrees. So we can line up the vertex of a linear pair of angles. In this case, I have ABC here, right here, ABC. And why don't I just go ahead and label another point over here. Let's call this D. I'll put D out here. And you can see we have a linear pair that we can measure right off the protractor. ABC is an obtuse angle, and from the scale it looks to be, well, I'd say 146 degrees. And then the acute angle CBD would be supplementary to 146, or 34 degrees. And the second angle postulate is called the angle addition postulate, which we've already been using. And just like the segment addition postulate, that just means that the whole angle is equal to the sum of its non-overlapping parts. So if we look at our drawing here, ABC is the large angle here, and that's made up of two smaller non-overlapping angles, ABD and CBD. So we can write the angle addition postulate here. The measure of angle ABC is going to equal the measure of angle ABD plus the measure of CBD. And here we have, I don't like the mess there, and here we have the some algebraic expressions put in the diagram for us, and we could substitute that in. So we could say the measure of ABC equals ABD is given an expression x, and CBD is given an expression y. Therefore, the large angle is going to be the sum of those, x plus y. And you can see that marked in the diagram. Okay, now I'm going to go through a series of theorems regarding angles, and we've looked at all of these before in Chapter 1. And remember, theorems are proven. Theorems are proven. They're not things that we take at face value and left unproven. So every single one of these we could write a two-column proof, and we will take a look at a couple of them. So the first one is the supplement theorem, and the supplement theorem says that if two angles form a linear pair, then they are supplementary angles. So here in our diagram, we see a linear pair, and so we could say that the measure of angle 1 plus the measure of angle 2 is going to sum to 180. The complement theorem, we have two non-common sides for adjacent angles, and they're forming a right angle as noted in this diagram. So therefore, the measure of angle 1 plus the measure of angle 2 is equal to 90 degrees. Think C for corner and S for straight. That's how I remember those. Moving on, we've got the congruent supplements theorem. That just states that if two angles are supplementary to the same angle, they must be congruent. And I think that should be obvious to everyone. So if we look at this diagram here, angle 1 is supplementary to angle 2, and angle 2 is supplementary to angle 3. So let's write that down. So the measure of angle 1 plus the measure of angle 2 is 180, and the measure of angle 2 plus the measure of angle 3 equals 180. Therefore, and we can write a little two-column proof on this, we would say that angle 1 and angle 3 are congruent. Likewise, the congruent complements theorem All that means is if two angles are complementary to the same angle, then they must be congruent. So over here in the diagram, we have angle 4 is complementary to angle 5. Angle 5 likewise is complementary to angle 6. Therefore, 4 and 6 must be congruent. So let's write that down. So the sum of angle 4 and angle 5 is going to equal 90 degrees, and the sum of angle 5 and angle 6 is 90 degrees. Therefore, and I'm going to abbreviate that. These little dots stand for therefore, angle 4 and angle 6 must be congruent. And hopefully you're already seeing, I hope, that you can look at, whoops, I forgot my 0 here. Hopefully when you look at this, you could imagine what a proof might look like to prove that 4 and 6 must be congruent. We'll do a couple of those. And the vertical angles theorem states that if two angles are vertical angles, then they are congruent. So here in our example, we have angles 1 is vertical to angle 3, so they are congruent. And angle 2 and angle 4 are vertical angles, so they are congruent. Therefore, their measures are equal. Now let's take a look at some right angle theorems. Again, all of these could be proven, and all of these we've looked at before. Perpendicular lines intersect to form 4 right angles. So here we've got perpendicular lines, A and C and DB. So let's write that as if AC is perpendicular to DB, then we would say angles 1, angle 2, angle 3, and angle 4 are right. All right angles are congruent. And again, we would say if angle 1, angle 2, and angle 3, and angle 4 are right, then they're all congruent. They're all going to equal 90. Perpendicular lines form congruent adjacent angles. What does that mean? If these lines are perpendicular and those angles all become congruent and right, well, if any one of the combinations are linear pairs, and if we're splitting 180 degrees into 2 equal halves, then they would all be 90 degrees and therefore congruent. So if we ever have perpendicular lines, then all the adjacent angles are going to be 90 and therefore congruent. So we could say if AC is perpendicular to DB, then, and we can go through all the combinations. Angle 1 is congruent to angle 2. Angle 2 is congruent to angle 4. Angle 4 is congruent to angle 3. And angle 3 is congruent to angle 1. And they are all adjacent angles. If two angles are congruent and supplementary, then each angle is a right angle. So for example, if angle 5 is congruent to angle 6 and angle 5, I'll write it as an equation, plus angle 6 equals 180, then angle 5 equals angle 6, and they are 90 degrees. Finally, here on the right angles, if two congruent angles form a linear pair, then they are right angles. So you couldn't have two congruent angles that are forming a line having any other value other than 90 degrees. So example, angle 7 plus angle 8 equals 180 degrees, and angle 7 equals angle 8, then angle 7 equals angle 8 equals 90 degrees. They are right. Okay, in the same way that we applied properties of congruence, properties of equality to pure numbers, we applied the same type of concepts to segments, and we called them properties of segment congruence. The same exact properties apply to angles. We have the reflexive property. Here we could say angle 1 is congruent to itself. Symmetric property. Angle 1, if angle 1 is congruent to angle 2, then we can flip those around. Angle 2 is congruent to angle 1. And finally, transitive, if angle 1 is congruent to angle 2, and angle 2 is congruent to something else, in this case angle 3, then we can transfer that value across. Angle 1 would be congruent to angle 3. So same type of properties we've been applying to everything. All right, let's try our first example. Let's prove one of the theorems, since they all can be proven. Let's take a look at proving the congruent supplements theorem. Okay, given angle 1 and angle 2 are supplementary, and angle 2 and 3 are supplementary. Prove that 1 and 3 must be congruent. Try to draw a sketch always first. So let's draw angle 1 and 2 as supplementary. Maybe the easiest way to do that would be to draw a linear pair. So let's say 2 and 1 here are supplementary, and angle 2 is also supplementary to angle 3. So I'm going to continue that line down and make 2 and 3 a linear pair as well. Now we have to prove that angle 1 and angle 3 are congruent. Alright, so let's start with the given, and you're going to want to write the given in exactly the way it's been provided. So angle 1 and angle 2 are supplementary, and sometimes that feels a little tedious to rewrite everything, but it is what it is. And angle 2 and angle 3 are supplementary. So all that is the given. Now we want to prove that 1 and 3 are congruent. Well, what do we do with information about supplementary angles? First thing we would do is write an equation. So angle 1 plus angle 2 would sum to 180 degrees. And angle 2 plus angle 3 would sum to 180. And that's the definition of supplementary angles. So you can write something fancy like supplementary angle theorem, but I just like things simple. So definition of supplementary angles is that they sum to 180. Keep it simple. I'm going to abbreviate. Okay, well, if this quantity here to the left equals 180 degrees, and this quantity equals 180 degrees, then they must equal each other. So I could put angle 1 plus angle 2 must equal angle 2 plus angle 3. And that is the transitive property. And you can see here in our equation that angle 2 is on the left and angle 2 is on the right. So if I subtract that from both sides here, I'm going to do it vertically, since all of you in class are telling me you don't like the way the textbook is doing everything horizontally. We can do the subtraction property of equality. And we would end up with angle 1 equals angle 3. And you can either leave it like that, or if you wanted to leave some kind of last statement here, you could say combine like terms or even simplify, I would accept. And there you have it. We have proven our first theorem. Example 2. In the figure, angle 1 and angle 4 form a linear pair. The measure of angle 3 plus the measure of angle 1 equals 180. Prove that angle 3 and angle 4 are congruent. Okay, we have a lot of given to rewrite here. Angle 1 and angle 4 form a linear pair. And the measure of angle 3 plus the measure of angle 1 equals 180. So that's our given. And it's difficult to take this information and mark the diagram. So that becomes a little bit tricky, so we're just going to leave it as that. Now we want to prove that 3 and 4 are congruent. Well, if angle 1 and angle 4 form a linear pair, we can do something with an equation there. We could say the measure of angle 1 plus the measure of angle 4 is going to sum to 180. That's the definition of a linear pair. They are supplementary. And we have two equations here now. So if this sum here equals 180 and this sum equals 180, well, they must equal each other. So I can write that as an equation. Measure of angle 3 plus measure of angle 1 must equal the measure of angle 1 plus the measure of angle 4. That is the transitive property. Sorry about my phone making noise here. Oh my goodness. Somebody's trying to get hold of me. Okay, so hopefully you see, again, just like the last proof, that we have the same quantity on the left and the right side of the equal sign. Therefore, we can subtract those. And I'm going to subtract them now. So we've got the measure of angle 3 plus the measure of angle 1 minus the measure of angle 1 equals the measure of angle 1 minus the measure of angle 1 plus the measure of angle 4. Subtraction property of equality. We are subtracting the same thing from both sides of the equal sign. And finally, we could see that these would cancel, and we have the measure of angle 3 equals the measure of angle 4. And you could just say simplify or combine like terms. Let's keep it simple. Simplify. And there we have it. We've proven that angle 3 and angle 4 equal each other. Now there's one last step we could do. It's that little nitpicking step. If the measures of angles are equal, then they are congruent. So we could then just make a final step and say angle 3 is congruent to angle 4, and that's just the definition of congruency. Equal measure, they are congruent. Okay. Okay, let's take a look at example 3. In the figure, angle NTR and RYA form a linear pair. Let's pause there because I noticed here I have a typo. There is no point T anywhere in this diagram. So what it was supposed to have been is NYR. So this angle here, apologize for that. Please replace that with when NYR. Okay, so angle NYR and RYA form a linear pair. Angles AXY and AXZ form a linear pair. And finally, RYA is congruent to AXZ. Prove that NYR and AXY are also congruent. So let's first write down the given. So angle NYR and RYA are a linear pair. And angles AXY and AXZ are a linear pair. Those are tough to mark on the diagram. However, we can mark the congruency here of RYA is congruent to angle AXZ. All of that is the given, and let's mark RYA, this angle here, is congruent to AXZ, so this angle here, so we can mark that. Okay, so hopefully, with the experience of the last couple of proofs, when we see a linear pair, we're going to immediately write an equation. So the measure of NYR plus the measure of angle RYA is going to sum to 180. And likewise, the same thing for the next row. AXY plus the measure of AXZ is going to sum to 180. And that is the definition of a linear pair. And just like the previous examples, if this quantity here on the left equals 180, and this quantity here on the next row equals 180, they equal each other. So I'm going to put them equal to each other. The measure of NYR plus the measure of RYA is going to equal the measure of angle, and I dropped this one here. Actually, I made a little mistake here. It's the angle AXY, measure of AXY plus the measure of AXZ. So if they both equal 180, then they must equal each other. Transitive property of equality. Now take a look at anything here that we can try to cancel out or subtract out. NYR is over here on the left. Is NYR over here? No, it's not. RYA is over here on the left. Do we see RYA over here on the right? No, we do not. So we don't have anything readily available to use the subtraction property of equality on. But we do have a piece of given information that we have not used yet. So we can substitute in one of these for the other and try to get some kind of cancellation. The question is, which one do we want to do? And in order to help answer that, we're going to just look at what we're trying to prove. So we're trying to prove somewhere down here, I'm going to write it, that the angle NYR is congruent to angle AXY. So we know here that we want NYR left. We don't want to cancel that out because that's what we're trying to prove. And AXY here, we want that left. So we know that's not going anywhere. So in which case we want to try to cancel out these here, and then we can get these two left to where we're trying to obtain our conclusion. So that should help us just kind of home in on what we want to get rid of. And up here in the given, we see that RYA and AXZ are congruent. So it really doesn't matter which one you swap out as long as you choose one. So I'm going to say that the measure, I'm going to go ahead and just write the subtraction property of equality right. Well, no, first I have to go ahead and swap out. So NYR, I'm going to change color here to make it obvious. I'm going to replace RYA with something that's equal to it. So I'm going to replace that with angle AXZ equals measure of AXY plus, and I'm just going to make this highlighted in the same color. So hopefully you can see that the only thing we did there is substitute. That was pure substitution. We replaced one value with another because they are equal. At this point, we can go ahead and subtract. I'm going to do it just in its own row. I'm going to subtract out the measure of AXZ from both sides of the equal sign. That would be subtraction property of equality. And we end up with the measure of NYR equals the measure of angle AXY. And you could say combine like terms or simplify. I'll say combine like terms. And finally, if the angle measures are equal, then they are congruent. And that is just the definition of congruency. I'm going to abbreviate here. Now somewhere along here up in this area I got a little lazy, and maybe a few of you have noticed it. So when I did the substitution, technically here these angles are congruent, therefore I should take the extra little step to say that their measures are equal before I go ahead and substitute. But I'm not going to take points off for these very small details in your proofs, as long as you can use the properties of equality and get to the goal. I'm not going to be too focused on those little nitpicky items. But anyway, hopefully you can see that this is all about finding ways to use the subtraction property of equality and use the transitive property of equality to simplify things down to where you want to get to. Okay, final example, example 4. Prove the right angles theorem. And that states that if two angles are congruent and supplementary, then each angle is a right angle. Okay, so remember the if part of the statement is the hypothesis, that's the given. And the then part of the statement is the conclusion, and that's what you're trying to prove. All right, so let's write down our given. We have two angles are congruent, and the same two angles are supplementary. And that's the given. And let's go ahead and use these labels over here in the diagram, angles 5 and angle 6. So we have angle 5 is congruent to angle 6. Let's mark that. Okay, and that's, no, it's really part of the given, but we're translating it into a statement of congruency. So let's just write statement of congruency. And if they're, we might as well be proper here, if they are congruent, their measures are equal. Definition of congruency. Okay, the same two angles are supplementary, so we would translate that as the measure of angle 5 plus the measure of angle 6 sums to 180. That's the definition of supplementary angles. I'm going to abbreviate here. Okay, so let's take a look at what we can do here. We've got two equations here, really. These two angles are equal, and we have a second equation here where their sum is 180. Well, we can swap one for the other, so it doesn't matter which one you choose. Let's go ahead and look at angle 6. So we've got the measure of angle 5 plus the measure of angle 5, because I'm swapping that out, equals 180. That is just substitution. And I've got two of these here, so I'm going to say two measures of angle 5 equal 180. Oh boy, that's messy. And you could say combine like terms. We just combined 1x plus 1x is 2x, basically. And let's go ahead and divide both sides by 2. So we end up with, well, we might as well write that right under here, division property of equality. We divided both sides by the same quantity, and we end up with the measure of angle 5 equals 90 degrees. Simplify. And if an angle equals 90 degrees, then that angle is a right angle. So angle 5 is a right angle. By the way, angle 6 is also a right angle since they are equal. So let's make that conclusion together. And the reason for that is the definition of a right angle is that its measure is 90 degrees. All right, hope this helps you work your way through some angle theorem proofs as well as other proofs involving angles. Thanks for listening. Please subscribe.